Welcome to Hartman Math. Today we're going to look at parent functions. Before we get there, 3 warm-up problems to work on here, 1 more to follow. I'll go ahead and pause the video here, work through these 3 first. See you in a bit. Alright, so number 1, we've got 2 parts here. Evaluate f of 1, f of 2, f of 1. Since it fits this condition, absolute value of 4 is 4. F of 2 fits this condition. Square root of 9 is 3. For part 2, is the function odd, even, or neither? Show it algebraically. We would do g of negative x. So 3 times the absolute value of negative x. Well, the absolute value of negative x is the same thing as the absolute value of positive x. And here, when we square negative x, we get x squared, so minus x squared. That is the original function. We need to say it's the original function, equals g of x. Therefore, we can conclude it's even. And practice on the difference quotient. You would get 4x plus 2h minus 3 under the condition that h cannot be 0, since we cannot divide by 0. Here's problem number 4. Here's a graph. We've got time on the horizontal axis, number of people on the vertical axis, and you need to come up with a story that describes each part. And you might want to label the parts A, B, C, D, E. So pause the video here, come up with your story, come back in a minute. All right, obviously we could have a lot of different stories, but maybe one possibility is, and it's really important that your story describes why the slopes of the lines are what they are. Why is it not the slope small here and then large here and so on. So one possibility might be this is before the fair is open and we got employees coming in, and then they open the doors, so obviously we got a lot of people coming in. And then maybe here it gets really, really hot, so we got a few people leaving. And now we got to describe why does it go all the way down to 0 right here. Maybe it could be someone called in a bomb scare and everyone's got to leave. And then the bomb squad gets there to come check things out. Or maybe you just said, you know, a little more normal, closing time, and then they brought in the cleaning crew. Something like that. But make sure your story tells basically why the slopes are what they are. All right, this is lesson 1.6, a library of parent functions. So we'll start with just a linear function where we're given some information. We're given 2 function values, and we know that it's linear. Given the fact that we have 2 function values, we can find the slope of the line using the slope formula. So the slope formula, m, or slope, is equal to y2 minus y1 over x2 minus x1. We get negative 3/2. So now, since neither of these points is a y-intercept, we're going to use point slope form. You can pick either one. So I chose this one, y minus here is equal to our slope times x minus negative 2. Distribute. Add the 5 so that we do finish out in y equals mx plus b slope-intercept form. And since it was f of x here, let's change it back. F of x equals negative 3 over 2 x plus 2. So now we're going to look at this library of parent functions that we can use. We've got a constant function, which would be horizontal, f of x equals c. F of x equals x is also linear, but that has a slope of 1 and a y-intercept of 0. And that is called the identity function, in case you need to know the name for a homework problem. We've got the squaring function, which is just our very standard quadratic function. f of x equals x squared. Here that we're calling it the squaring function, U-shape, so it's a parabola. Different things about that we know already from Math 2. The domain is a set of all real numbers. The range is positive numbers and 0. From previous lesson, it's even because it's symmetric about the y-axis. Has a intercept at 0, 0. That's both an x-intercept and a y-intercept. It is decreasing here. It is increasing here. We talked about the symmetry, which kind of talks to it being even. It has a relative minimum at 0, 0 because it changed from decreasing to increasing. So those are some of the things about the squaring function. We've got the cubic function, x cubed. So some of the characteristics there. It goes forever left and forever right, so the domain is the set of all real numbers. The range, since it goes down forever and up forever, that's also all real numbers. It is odd because of the symmetry here, that if we spin it around the origin, that it's 180 degrees halfway around, it's going to look exactly the same. So it's got point symmetry about the origin. That's what makes it odd by the graph. We have an x and a y-intercept at 0, 0. It's always increasing throughout the domain. So from negative infinity to positive infinity, it's always going up. And that's the cubic function. We've got our square root function. In the square root function, important to know key points. 0, 0 and 1, 1 would be key points. If we went back for a moment, key points here that you would also want to be aware of: 1, 1, negative 1, comma, negative 1. All right, so characteristics about the square root function. The domain is positive numbers and 0, so non-negative from 0 to infinity, bracket 0, infinity, parentheses. Range, kind of the same thing, 0 and going up, so non-negative real numbers there. Intercept at 0, 0. It's increasing throughout. Remember, for increasing and decreasing constant, we always use parentheses. So 0 to infinity is where it is increasing. The reciprocal function, f of x equals 1 over x. Looks like this. Key points, 1, 1, negative 1, negative 1. The domain is everything except for 0. So negative infinity to 0, 0 to infinity. We have a vertical asymptote there because you can't divide by 0, so x can't be 0. The range, the same thing. We got positives here, we got negatives here, but since it never touches the x-axis, 0 is not in the range. It is odd because if we spin it halfway around, this one goes to there, that one goes to there, so it's an odd function. There are no intercepts. It's always decreasing, so both branches or both parts, it's decreasing here and it's decreasing here. Now, we already talked about the symmetry. Step and piecewise defined functions. The most popular step function is the greatest integer function. It's denoted by, and it kind of looks like these double brackets. So that's what represents the greatest integer function. And it's defined to be, whatever x is, it's the greatest integer that is less than or equal to the x. So in this case, if we're evaluating some values, the greatest integer function of negative 1, since negative 1 is equal to negative 1, you get negative 1. Negative 1/2 is not an integer, so we actually just drop down to the next lowest integer, or think on the number line to the left, so that drops down to negative 1. 1/10 is between 0 and 1, so we drop down to the integer below, which would be 0. 1.5 is between 1 and 2. We drop down to 1. 1.9 is between 1 and 2. We drop down to 1. It's not what it's closest to. It's the greatest integer, so we always go the integer that's less than or equal to, so think to the left. So if we were to graph all of this, it looks like this. Here's the step part of that. So characteristics, the domain, we can plug in any number, so the domain is all real numbers. But the range, the y values, only integers. So the range is 0, 1, 2, 3, 4, -1, -2. Can't get an output value that's not an integer. All right, we have a y-intercept at 0, 0. We've got x-intercepts all the way along here in that interval. It's constant between any consecutive integer values, and it jumps 1 unit at a time. So example number 2, let's see if we can evaluate some of these. F of x equals the greatest integer of sum x plus 4. Let's try f of -3/2. So -3/2 plus 4 is 5/2. So greatest integer of 5/2. Since that's 2.5, we're talking about between 2 and 3. We drop down to 2. F of 1. 1 plus 4 is 5. That is an integer, so we'll stick with 5. -4.05. We'll add that to 4. We get -0.05. Greatest integer of that. That is between -1 and 0, so we drop down to the -1. Example number 3, graph a piecewise defined. So we've been evaluating these. Now let's see about graphing. So we've got f of x. We've got a y equals mx plus b situation here. So we're going to graph a line, but we're only going to do so for x values that are less than or equal to 2. So what we might do is just kind of think about what is this going to look like. Well, if we had no restrictions, we'd have a y-intercept of 2. And then we'd have a slope of down 1, right 2. And so on. But we don't want to be over here. We have to be our x values that are less than or equal to -2. So we need to extend to the other side. So if we continue this pattern going over here, so we want the one where x is -2. Here's our x coordinate of -2. So there's our, essentially our starting point there, and going left. So we want that part. We don't want any of this. And then over here, we've got a parabola, x squared minus 3, standard parabola, which would usually have a vertex at the origin, but shifted down 3. So here, as you should have a lot of experience already graphing parabolas, and then we want that parabola greater than -2. So here's the -2. It has to be greater than that. So we would show that on the graph with an open circle. And then everything else here going to the right. So we got that part. And we got that part. And there's our graph. We could talk about domain. Even though there is a closed point here, so there is a point at -2. So the domain would be parentheses -infinity, comma positive infinity, parentheses. The range is everything above, on or above -3. So bracket -3, comma infinity would be the range if we were asking for things like that. All right. Checkpoint. Go ahead and pause the video here and graph this piecewise function. Resume when you're ready. All right, we've got 2 lines. I think they actually connect in this case. So we've got that first one goes to there, open circle there. The y-intercept is -1 up to right 3. And then this one, y-intercept of 4, and then down 1, right 1, down 1, right 1. And it starts there. The close point fills in the open point. So I've seen this before You don't want to do that. There's no meaning there. The closed point just fills in the open point in this case. And we got our line going that way. All right, so just a recap of the parent functions that we're looking at here. We've got our constant function, horizontal. We've got our identity function, which is linear. Our absolute value function, square root function, squaring, cubic, reciprocal, and greatest integer function. That's it for today. I'll see you next time.